Artificial intelligence has already helped astronomers discover planets that don't technically exist in our data. Worlds that appear only as a 1 in 10,000 statistical blip in noisy starlight, but which turn out to be real places, orbiting real suns light years away. To understand where this is going, we need to zoom out, way out, and see AI not just as a clever tool, but as a new kind of sense organ for our species. For most of human history, our picture of the universe was limited by our biology. Our eyes can see only a tiny slice of the electromagnetic spectrum. Our brains can only track a handful of variables at once. And our lifetimes are too short to watch stars live and die. Telescopes, spectrometers, and spacecraft extended our reach, but they all produced one thing: data. Petabytes of photons turned into pixel values, spectra, and signals. AI changes what we can notice in that ocean of data. It's not magic, it's statistics at scale, but it lets us ask questions that would have been physically impossible for any one human or any team of humans to even formulate, let alone answer. Let's start with something concrete: exoplanets, planets orbiting other stars. The most productive way we've found them is the transit method. You stare at a star for months or years and look for tiny, periodic dips in brightness when a planet crosses the star's face, blocking a fraction of its light. For an Earth-sized planet orbiting a Sun-like star, that dip is about 0.01%, 1 part in 10,000, and it lasts only a few hours out of an entire year-long orbit. Missions like Kepler and TESS have recorded the brightness of hundreds of thousands of stars, taking a measurement every few minutes for years. That produces light curves with millions of data points per star and literally billions overall. Traditional algorithms can search those curves for dips, but they have to be told in advance what a transit should look like: how long, how deep, how periodic. AI, specifically deep learning models like convolutional neural networks, can instead be trained on examples of known planets and known false alarms, and then learn the subtle statistical fingerprints that distinguish a real planetary transit from, say, star spots, instrumental noise, or random fluctuations. One striking example came when researchers reanalyzed Kepler data that had already been combed by classical methods. Google's team, working with astronomers, trained a neural network called AstroNet on thousands of labeled light curves, planet candidate versus non-planet. When they unleashed it on the full dataset, it found additional planets, like Kepler 90I, a hot, rocky world roughly 30% larger than Earth, orbiting its star once every 14.4 days. The planet's transit signal was so faint and so entangled with noise that earlier automated searches had written it off. The neural network, however, learned correlations that weren't explicitly encoded in any human-written rule: the way genuine transits repeat with nearly identical shapes, the way noise tends to vary asymmetrically, the way multi-planet systems imprint multiple overlapping periodicities. This wasn't a single fluke. Across the dataset, AI recovered dozens of viable candidates that standard pipelines had missed. That's a taste of the near future. As telescopes like Plato and the Nancy Grace Roman Space Telescope come online, AI will be the first eyes on their data, triaging billions of light curves to tell human astronomers where to look more closely. But discovering more planets is just the first act. The real revolution begins when AI stops being just a pattern recognizer and becomes a hypothesis generator, a system that can propose, "This looks like none of our labeled categories, and here's why." Today, a lot of machine learning in astronomy is supervised. We give the model examples and ask it to classify new data into those known buckets: planet or not a planet, spiral galaxy or elliptical galaxy, flare or no flare. The frontier is unsupervised and self-supervised learning, where the AI is asked to compress and reconstruct data without human labels, and in doing so, it discovers its own internal coordinates, its own map of what kinds of things exist in the data. Imagine feeding in millions of galaxy spectra, the detailed fingerprints of the light emitted by galaxies across many wavelengths, and asking the AI simply to organize them into clusters that make sense to it. It might rediscover known classes, star-forming galaxies here, quiescent ellipticals there, active galactic nuclei over in this corner. But it might also highlight outliers, objects that don't sit comfortably in any group, whose spectra feature combinations of emission and absorption lines we've never catalogued. Those outliers are often where the most interesting physics lives. Strange black hole feeding regimes, transient events caught mid-explosion, or entirely new phases of galaxy evolution. This ability to algorithmically say, something weird is happening here, has a name: anomaly detection. And as telescopes move from taking single snapshots to running surveys that scan the whole sky over and over, anomaly detection will become one of AI's most important jobs. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, is a good example. When it comes fully online, LSST will image the entire visible sky every few nights, generating about 20 terabytes of data per night, and detecting around 10 million transient or variable events every 24 hours. A transient here means anything that changes: a supernova, a variable star pulsing, an asteroid streaking by, even things we haven't yet named. No human team can review 10 million alerts a day. Even sorting out which 100 deserve rapid follow-up with other telescopes requires automation. Rule-based filters are too brittle. If you only look for things that match your predefined templates, by design you're blind to the truly new. Machine learning models can instead be trained on the full history of sky variability to learn what normal looks like at many timescales and brightness levels, and then flag candidates that deviate in statistically significant ways. Some of those deviations will be junk, bad pixels, cosmic rays hitting the detector, but buried among them could be the optical counterpart of a gravitational wave event. The first light from a pair of neutron stars colliding hundreds of millions of light-years away, or the afterglow of a gamma-ray burst from the collapse of a massive star. AI isn't just helping us explore distant galaxies, it's also becoming central to monitoring the cosmic neighborhood that can directly affect life on Earth. Take asteroids. There are hundreds of thousands of known near-Earth objects, NEOs, whose orbits bring them within 1.3 astronomical units of the Sun, roughly the distance from the Sun to Earth, plus a bit. We've mapped most of the kilometer-scale ones that could cause global damage, but there are many smaller, 100-meter scale objects that could still cause regional devastation if they hit. Surveys like Pan-STARRS and the upcoming NEO Surveyor mission scan the sky for moving points of light, then fit orbits to those detections using celestial mechanics, Newton's laws applied to multiple bodies. AI enters in two places here. First, in sifting through the raw images to distinguish genuine moving objects from detector artifacts, satellites, and noise, convolutional networks are already being trained to classify streaks and blips with high reliability. Second, in prioritizing which newly discovered objects need urgent follow-up. Orbital calculations have uncertainties. They're probability clouds, not exact paths. Bayesian inference combined with machine learning can estimate, in real time, how additional observations would shrink those clouds, and which asteroids have even a tiny but non-zero probability of intersecting Earth's orbit over the next century. In practice, that means an AI system can tell human observers, if you only have time to point your telescopes at 20 objects tonight, these are the ones that will most improve our planetary defense. Now, protecting Earth from rocks is one thing. Protecting it from ourselves is more complicated. And AI has a role there too, in ways that loop back to our cosmic perspective. Satellites in low Earth orbit constantly monitor our planet's atmosphere, oceans, and land. They measure things like atmospheric CO2 concentration, methane leaks, sea surface temperature, forest cover, and ice sheet thickness. These measurements are often multispectral or hyperspectral. Instead of just red, green, and blue, instruments record tens or even hundreds of narrow wavelength bands. Each band encodes different physical information. For example, how strongly chlorophyll in plants is absorbing light, or how water vapor is affecting infrared radiation. The raw data are enormous and messy, influenced by clouds, aerosols, instrument noise, and changing viewing angles. Machine learning models, from random forests to deep neural networks, are increasingly used to turn this torrent into meaningful, timely maps. Where deforestation is accelerating, which wetlands are emitting methane, how quickly glaciers are retreating. Some systems, like Google's flood forecasting initiative, go even further, using AI to predict river flooding days in advance by combining satellite data, weather forecasts, and hydrological models. At a larger scale, Earth system models simulate the climate with grids of cells tens of kilometers wide, using equations of fluid dynamics, radiation transfer, and chemistry. These models are extremely computationally expensive. AI is starting to act as a surrogate model for some of the slowest processes, like cloud microphysics. Instead of computing every droplet, a neural network, trained on high-resolution simulations, can approximate the net effect of clouds on temperature and humidity in each grid cell. This can speed up climate projections by orders of magnitude, allowing us to explore many different futures and policy scenarios much faster than before. If AI is becoming our nervous system for the planet, what about beyond the observable universe? Beyond what we can directly see, even with perfect telescopes? Here, AI merges with theoretical physics. Consider dark matter, the invisible mass that makes up about 85% of the matter in the universe, detectable only through its gravitational effects. Cosmological simulations like Illustra's TNG and Millennium simulate billions of particles evolving under gravity and sometimes hydrodynamics to model how dark matter and normal matter clump into filaments and halos over billions of years. These simulations are expensive. A single high-resolution run can consume millions of CPU hours. And yet, we'd like to explore many different cosmological parameters. What if dark matter is slightly warmer, or interacts weakly with itself, or decays over time? AI emulators, generative models such as generative adversarial networks and score-based diffusion models, can be trained on a limited set of full simulations to learn the mapping from initial conditions to final large-scale structures. Once trained, they can generate new, statistically consistent universes in seconds, allowing researchers to scan the parameter space much more thoroughly. In effect, the AI becomes a compressed, differentiable version of the cosmos, a fast-forward button for structure formation. We're also beginning to use machine learning to invert observations. Given the cosmic microwave background map, or a 3D distribution of galaxies from a survey, what initial quantum fluctuations in the early universe would most likely have produced what we see? That's a monstrously high-dimensional inference problem, but neural networks optimized with techniques like variational inference and normalizing flows are starting to make it tractable. All of this raises a deeper, almost philosophical possibility: AI as a collaborator in theory-making itself. Right now, most physics-aware AI is still fundamentally a function approximator. Given inputs and outputs, it learns a black box mapping. But several research groups are working on systems that can propose symbolic models, actual equations. One approach, called symbolic regression, searches the space of mathematical expressions, combinations of operators like plus, minus, multiply, divide, exponentials, and trigonometric functions to find compact formulas that fit data well. In 2009, the Eureka system famously rediscovered Newton's law of motion from a pendulum dataset. Today, more advanced methods combine neural networks with symbolic search, using the network to suggest promising structures and the symbolic engine to refine exact forms. Imagine feeding such a system the orbits of stars in the Milky Way's halo, and asking it to derive the simplest underlying law that explains their distribution, potentially hinting at non-Newtonian effects, modified gravity theories, or specific dark matter halo shapes. But the idea that our next big physical insight could begin as a pattern noticed by a machine and then translated into mathematics we can understand is no longer science fiction.